All right. So, what we're going to talk about today is atmospheric pressure, the weight of the air. So, what is the significance of that variations in the pressure in both horizontal and vertical? So, let's take a look at that a little bit. So, air exerts a force. Uh, what that means is it's pushing against you constantly. If you go up higher on the tops of the mountains, uh, kind of an interesting experience I had out in the Rockies. Down in the valley, before you go up, we were at about 5,000 feet, and the wind was blowing fairly hard, not real hard that day, but you could really feel it. It was pushing you around. When we went up to about 13,000 feet that day, air pressure is a lot less. There's a lot less molecules of air up there. And even though the wind was blowing stronger, it didn't feel as hard. That's because the force of the air was less because there was less mass. There was acceleration, sure, but the mass, the number of air molecules was less. So Dalton's law says that if you have a mixture of gases and each one of those gases has a certain pressure, the total number of those gases together will be the pressure of whatever that column of air is. So in the Earth's atmosphere, nitrogen, oxygen, carbon dioxide, water vapor, each one of those is a pressure that makes up the total. So air pressure depends on the mass of molecules. So in other words, if I take a space and if I were to draw a 1 meter cube, how many molecules are in that cube? And the kinetic energy of those molecules would be a pressure. So I don't know how many molecules are in that cube, but if there were more molecules, the more it would weigh. The more kinetic energy there is, the more it would weigh. So kinetic energy, as we know, is related to temperature. So that would say, oh, the hotter that little cube is, the more it would weigh. Well, air's a little different than many things. Air is compressible. So what that means is it can expand or contract. The number of molecules in that little 1 meter will change. If there is more heating, some of those molecules are going to go out of there. So it actually lowers the air pressure when it gets hotter. When it gets colder, more and more molecules are going to be in that little cube, and the mass will be enough to weigh more, and you'll get more air pressure. So that is something that's different than a lot of substances. The average sea level pressure in English units is 14.7 pounds per square inch. So every square inch of your body has 14.7 pounds approximately pushing against it all the time. So why don't you collapse? Why don't you just, sink together? Because the air inside of you is pushing back out at the same pound. How do we measure air pressure? We use mercury barometers with the old school stuff we used. Now we have aneroid barometers and all. And we make adjustments. We really tweak on these to make them as accurate as possible. Airplanes really need this because if you're flying into an airport, you want to know exactly what that pressure is so your altimeter is exactly right and you know exactly where the ground is going to be when you're coming down. Here is a conversion of different units we use for pressure. And kilopascals or millibars basically are what I like to use. But you'll get used to inches of mercury and you'll probably see me talk about millibars. So here we get into the drop of pressure in compressible air. So the higher up you are in the atmosphere, there's less air. But air is pushing down because of gravity from above. So more and more air is compressed in the lower levels. That is why air pressure changes faster the first 1,000 feet you go up, And then the next 1,000 feet, it doesn't change quite as much. And then the next 1,000, it doesn't change as much again. So as you're going up through the atmosphere, the pressure is actually changing slower with the height you get. But here near the Earth, it changes pretty quickly. Also, one of the interesting things about pressure variations is, say a storm is coming at your house, and we're going to quickly see a graph here of that. You see the pressure dropped a little bit. It went from 10, 13 millibars down to 1,008. So maybe 5 millibars of pressure as that low pressure moved towards you. However, in the vertical, basically you can go up 5,000 feet and have 150 millibars of air pressure difference. So the vertical pressure gradients are way more than they are in the horizontal. Yet the horizontal is what we use to track low pressures coming towards you and high pressures coming towards you. And they make a significant difference on the kind of weather you're going to have. We talked about rising air, but remember, the atmosphere is not a closed container. So therefore, the molecules will move out and away. And that is also why the troposphere gets thicker when you're down and near the equator than when you're up by the North or South Pole. The heating down there will push the molecules further apart. It pushes the troposphere higher up into the atmosphere. Less heating at the poles pushes the troposphere closer together. So in the wintertime, because it is so cold, the air is very dense. There's not as much kinetic energy. So if you want to go in the vertical, you're going to change pressure very quickly because you got a lot of molecules there at the bottom. So as you're going up, your pressure is going to drop much faster than it is in the summertime. And 500 millibars is basically halfway up. We think of 1,000 millibars as being at the surface. So 500 millibars is about halfway through the atmosphere. It'll be lower in the colder air. In the wintertime, it's significantly lower. In the summertime, it's higher. And interestingly, water vapor is less dense than normal air. So the more water vapor, the less dense the air is, and it's not as heavy. You don't think that. When you're out in a humid, sticky air mass, if the air feels heavy, but it's actually lighter than the dry air in the wintertime. Winds carry these molecules around. We have converging winds when airs come together, and we have diverging winds when winds are blowing apart. Blowing apart would just mean they're pulling molecules further away from each other. So if that's the case, then the pressure would be less where the winds are diverging, and the pressure would be more where the winds are converging. We've learned that winds change direction with altitude. Well, therefore, when you go up high in the atmosphere and if the winds are coming together, they're going to tend to push the air down towards the ground. So that is going to tend to increase the pressure at the surface. If you have the opposite effect, if winds are diverging aloft, then the ground, your winds are going to be trying to come together, but the air is going to be rising up. And you tend to wind up having low pressures. The ideal gas law, all it's saying is if I know pressure and temperature or density, two of the three, I can calculate the other. In the atmosphere, have you ever filled a tire with gas, with air pressure? When the air is coming out from that tire, it's expanding quickly. It gets pretty cold. By the same token, if you have a hand pump, I know probably none of you ever used those to fill a basketball or a soccer ball. But when you keep pumping it, you'll notice the cylinder gets hotter and hotter. That's because you're compressing the air. So compression warms it. So think about it. A cube of air. If it starts up high and moves down, it's getting compressed. Work is being done. It's warming. If the same cube of air goes up higher, it's expanding It's getting cooled. It's cooling. That in the troposphere is why temperatures decrease with height. And you can see here, the air is actually doing energy on it when it's compressing it, and the air is releasing energy when it's expanding. So if you know that, and you take a normal atmospheric pressure, you can calculate that if the air is dry, which means we're not talking about any latent heating, normally the air temperature would drop by 9.8 degrees Celsius per 1,000 meter, or 5.5 degrees Fahrenheit per 1,000 feet. So as you were going up in the atmosphere, walking your way up higher, the air is going to get colder. And that is the rate it's going to get colder. The air doesn't cool at that rate necessarily. Other factors play in. But that is as cold as the atmosphere can get in that meters because of the expansion. Now, when you get to the point where you have moisture in the atmosphere, remember we have latent heating. So if condensation occurs, heat is being released into the atmosphere. So instead of cooling at a 9.8, it only cools at 6 degrees. So that is why temperature curves in the atmosphere aren't always going to sit at 9.8 degrees Celsius. Clouds and other things mix in and change that. So now let's take a look. One thing I wanted to try to show. I wanted to show a change pressure. So we're going to look at sea level pressure. This is at Roanoke. And yesterday a cold front was approaching. So temperatures were dropping because a cold front is like a low pressure system. And you'll see they got all the way down to here, 1013.1, 1012.9. Cold front has passed. They're going back up. These are not huge pressure differences, but you can see how we can plot pressure each hour and see the change. And finally, I just wanted to show you today on the map, big high pressures over the Great Lakes. And you can see 1023 millibar, 1024 millibar. If I were to move that high, look around out to the west, there's a low out over western Texas, panhandle of Oklahoma, and it's 994 millibars. So 993 millibars is what the actual estimate is. So that is the difference between a high and the low pressure. You go out to California, there is some strong low pressure off the coast here. 1,004 millibars with more low pressure coming in. So you can see how pressures are changing around the U.S. So I hope you got a little bit out of this. Let me know if you have any questions this week.